It's like you can still see. Yeah, it still works. It's just. I did it the really old-fashioned way. I would write things down, and this was pretty much the last 2 semesters with COVID, with like online submissions. I would take a picture of my physical work, email it like I would take my photos with my phone, send it as an email,
Okay.
send my phone to my
So Cody is online. Cody, can you hear us? Go ahead.
Yeah.
Can you hear? I can't hear you. Say something.
Hello?
Hello?
Can you hear me?
Can you hear me?
Yeah, I can hear you. Can you hear me?
So I'm gonna mute your microphone. And if you have a question, just anytime unmute, start talking. Okay. So one person online today. That's all right. No problem. Okay. So today's lecture, huh?
Sure.
Okay. So today's lecture. So before I begin, sorry to ruin your fun, but I think I'm already recording. Okay, good. So today's lecture has nothing to do with aerodynamics. I'm going to sacrifice one lecture today to go over fluid mechanics, hydrostatics. If you know those things, you can go home now. If you feel confident, hey, Dr. H, I know that. Because I have done quiz 0 problem 2 and then quiz 2 already done. It's a piece of cake. I spent 5 minutes doing it. Go home. I mean it. I'm not kidding. Today's Friday. Go home. Question? Yes?
I did most of quiz 2, but I'm kind of stuck on part C.
Again, it's your decision. If you want to stay, you stay. If you want to go home, go home. How's that? Somebody please go home. Okay. Because somebody need to break on ice,
It's just weird to get.
No, I'm saying it. Professor saying go home.
Say all you want. It's weird.
Go ahead. Go ahead.
Will you go over like a little bit of how like the?
I'm not going to go over quizzes.
I know, but like
I'm going to lecture fluid mechanics. I'm going to sacrifice today's class going over fluid mechanics. I'm not going to talk anything about quiz.
But will you talk about
Quiz 0 is something you have to figure it out based on today's lecture.
Temperature variability from up to 3,600 feet.
Something you have to figure it out. That's right. So if you want to stay, you can stay. If you want to go home, go home. Everything's recorded, by the way. So you're not going to lose anything if you go, even if you go home. So please, somebody go home. Please. Nobody? Nobody?
Oh, I pay too much for this school. I'm staying. Almost had me there.
So basically, you chose to stay.
Yes.
Right? I didn't force you to stay.
Correct.
This is a free country.
That is correct.
If you want to do something bad, go ahead, do bad. Get the consequence. I don't care. But if you want something good to be given to you, including money, you do the right thing. This is engineering. If you do crappy job and your airplane crash and somebody died, nobody's gonna pay for it. Okay? They're gonna send you a bill. A big bill that you can never pay back. Do you have a piece of paper? Let's get ready to take attendance. If you don't have a paper, raise your hand right now. I give you another paper and make you up. Yeah, so everybody has a paper? Everybody has a paper? Okay, good. So let's just take attendance. Here we go. All right. By the way, Zoya? Zoya, okay. Zach, Darren, Robert, Heidi, Hunter, Jacob, Jaden, sorry, Michael, Ian, Peter, Anthony, sorry, Dick Chan, am I right? Yeah. Dick Chan, okay. Okay, Rob. The thingy. Yeah. Michael.
You know, maybe.
Marcelo. All right. So one last long look for the video. This is the class of today. And those are the people basically refused to go home, even though Professor said go home. All right, so Stephen Booth. Stephen, come forward, please. Stephen, come forward. You are in trouble.
Go, Steven.
Okay. So hopefully. Am I presenting? Okay. Go ahead.
So I'm Steven.
Hi, Steven.
Hi,
Steven.
So I'm part of Eagle Nautics. We're a club on campus. Next slide. So we're a DVF club, and we design RC scale like heavy lift aircraft, and we're part of the SAE Aero West design competition. Basically, in like the fall semester, we design the plane like with simulations and like design tools, and then we build it in like the spring semester. So if you're interested in joining, you can talk to me after class, and I can get your information.
You actually go to competition next year.
Yes.
April, right?
Yeah, it's in April.
And then it's in California, Los Angeles.
And that's where we fly the plane.
Yeah. So this is actually international competition. 2 years ago, before COVID, we were 17th or something in the ranking out of 75 or something. And then top 3 is all foreign people. Poland, China, something like that. Those are like a semi-professionals.
Team. Yeah, all throughout the country.
But the technical presentation, we were 2nd out of 75. So Embry-Riddle's name stands out for technical presentation because the design uses very solid foundation based on somebody's class. I don't know, aerodynamics one or something somebody's teaching. So it's theory based, and also simulations done, analysis is done, very solid, and then halfway convincing, hey, this must be flying. And then payload is insane. You have to carry like how many tanks ball you have to carry?
Last year we designed it to hold I think 15 pounds.
Something like that. You have to carry the hunk of metal in the middle of the body.
Soccer ball as well.
Soccer balls. Those are passengers, and hunk of metal is a baggage. It's insanely heavy airplane, short takeoff, it's crazy to handle. So lots of airplane actually crashes on site. You can see those things showing up in Los Angeles airport. I mean, it's not an airport, but Los Angeles. RC airport, Los Angeles. So it's a fun day. And then this team, this airplane, made it fly, didn't crash, and still surviving. You can see it today. By the way, the name of this airplane is Ron, name of the Dean of Engineering, Dr. Madra.
This was, I think, 2018?
Yeah, I guess 2 years ago. No,
Yeah.
2019.
Yeah, and then 2020.
Then 2020 was canceled because of COVID. Then we're gonna go up next year, April. So now is the time to join. If you are airplane enthusiast, if you want to design something, actually can fly, and then join the team. He needs lots of hands to help. And then we are funded so that we can send you to the Los Angeles and actually compete with other schools and other people from other countries. Those are not those are not students. Those are semi-professionals. This is cheating. But anyways, because Poland team, they show up like a week before and they kept practicing. That's cheating. But anyways, still we can compete with those people. Okay. Any question?
Just real quick, you can be like as involved as you want. So we can find like stuff for you to do, even if you don't want to do a lot of like engineering design. You can work on more of like the club management aspect, or you can just go full in and design the plane, like the structures and the aero, and so of the plane. So yeah.
Are you looking for people who have pretty extensive experience in this already? People who've dealt with scale size planes and stuff like that?
You don't have to have experience, but if you do, then
It's going to be welcomed if so, but I mean, it's not necessary. Yeah.
And I mean, if you just want to work on CAD, because we make every single part of the planes, there might be like 100 or so parts that we have to make in SolidWorks for the plane. So you can do that if you really love CAD. We use SolidWorks, so yeah.
Yep, SolidWorks. Yeah, anyways. All right, so thank you, Stephen. So like I said, today's lecture is 100% optional, and then this is not there. This is fluid mechanics, something you already know. Okay, so hydrostatics. This is one of the governing equations which is quite important. There are a few governing equations I have to point out in fluid mechanics. This is the first one. So there are a few governing equations which is kind of important things that the people always associated with, everything, all the equations comes from here type of equation. Hydrostatics, okay? Have you ever seen this equation? dP is equal to minus rho g dz.
Yes.
No, this is the pressure variation if the fluid is not moving. This can be applied for any type of fluid, including liquid and gas. Now, this is aerodynamics, so we are talking about gas, okay? So, if this is a fluid mechanics in liquid, there's one thing which you need to be aware of. If this is a liquid, almost all the time, this density is constant because it's liquid. So that actually making things super easy. That is called incompressible liquid, not moving. Okay? So you can go ahead right now, right here, tell me the equation of delta P if the density is constant. I saw the fluid mechanics. You've seen this before. Can you tell that? Go ahead. You can go ahead and try.
Is it rho g delta z?
Rho g delta z, correct? Yeah, hydrostatic pressure variation in liquid. Because density is constant, so the Ernie bird is trying to show here, let's say this is the height. And this is fluid. Could be liquid, could be gas, I don't care, but density never change. This is the height Z1, pressure is P1. This is the height Z2, pressure is P2. What is the pressure difference? Rho g delta z. Actually, negative rho g delta z. Because z is measured from here and up. So which pressure is higher? Pressure? Lower one? Of course. If you go all the way to the sea level, this is, let's say this is location A, okay? Because that's what I'm kind of referring to in my fluid mechanics notes. So I'm going to say standard sea level is right here. So the location A, sea level, okay? If Z1 equal to standard sea level, that means Z1 equal to 0. That is standard sea level pressure, PAPM. And you know the value. If it's a standard day, 14.7 psi. But if you go up and up and up and up and here, what is the pressure then? Negative rho g, this z. Okay. Do you think this is accurate?
It's idealized, so no.
Oh no, it's idealized. So if you keep using that kind of equation for really high altitude where airplanes flying, you may have extremely weird values, such as negative pressure or something. What kind of thing? Right? Obviously, it's not right. But this is one of the pressure variation equation first introduced in fluid mechanics. Do you remember that? I hope so. By the way, I'm going to make this like a, well, yeah. I'm going to make it smaller because I want to show you something else here too in the space given. So I'm going to open up another window. So this is the prerequisite fluid mechanics. Can you still see it? It's kind of small, but let's go to Unit B. This is my fluid mechanics notes. Go all the way down here. Look at this page. This is what I'm talking about, hydrostatic pressure variation. Okay, of course, in fluid mechanics, you're going to deal with liquid. So oftentimes, depths and height, those are always used interchangeably. But you can deal with the same kind of equation. Equation could be either based on the height or based on the depths. Either way, one is negative direction. Somebody was raising hand. I kept ignoring. Go ahead.
Yeah, so I was going to ask, if we are dealing with high altitudes, would we just do an integral, and then I'm assuming the density would be an equation?
I don't understand what you're talking about, but you already did an integral to find out this equation.
No,
right?
I'm talking about before, how you said you can't use the simplified version.
I don't understand what your question is. Simplified version, what is it?
So for, on that, yeah, when you said you can't use that for high altitudes, like going
You can use it to anywhere, but this is basically based on the assumption almost all the time in air. It's a wrong assumption. Density can never be constant in air.
So then would we use,
You can use this still.
would it be an integral with the density?
What's
as a
integral?
function?
What's integral? You integrate it to get this equation, right? This is the original equation. You integrate it, and then integration is done based on the assumption given. The assumption is density constant. So take a look, okay? This is what I'm talking about. You keep saying integral, that's correct, because starting from this equation, you're going to do this. Integral EP is equal to minus integral rho g dg. That's what you're doing. So this is always the starting point to get the pressure difference. How can you finish up right-hand side, especially this integral? You need to have certain condition to it. In this case, condition rho is constant, goes outside of integral. Condition g is constant because it's fluid mechanics, goes outside of integral. What is the result? Delta p is equal to rho g delta z minus. You did the integration to get that equation, get this equation, right? Now the question is, what is the condition for integration? Density constant. This is the condition of integration. Okay. So where can you find such a thing? This is the note. Unit B1 note of my fluid mechanics, page 4. I actually do the details of integration. So this is basically starting from small tiny element in the depth h or height z. You ended up having this equation. This is hydrostatic equation. This is a differential equation. Then next step, you have to integrate to get the pressure variation within, right? Well, that's what you're doing. You are integrating from this height to that height, then get the pressure difference. Pressure difference is an algebraic equation. Algebraic equation can only be given from original differential equation by integration. But integration can be done under certain different conditions. This condition, density constant, gravity constant. Well, that's easier. One goes outside. So delta P is minus rho G delta Z. That's what you got. And then you can find that right here. Fluid mechanics notes. Unit B1. Page what? I don't know. Page something like that. I don't know. You can find it. I post it for free for you. If you don't look at it, it's your problem. Okay. Anyways, I'm not the fluid mechanics guy, so just take a look at it and explore yourself and find out. Anyways, so okay so far. Okay so far. Okay. Okay. Good. That's actually a very good question there. I appreciate that. Integral is the key because you need to do integration to find out algebraic form of equation. The question is, how do you integrate? Next one, suppose, okay? Now we are dealing with density constant is very bad assumption. We know that. So density is not constant. Sure, of course, you know, we're talking about atmosphere. Density keeps changing. So, okay, so I have to carry density, this is a variable, into our equation. We cannot assume anymore density is constant. However, can we still assume ideal gas? Yes, I think so. More air is ideal gas.
Oh, yes.
At a point, yes.
Unless you go all the way to the outer space. So let's assume ideal gas. So basically, we're going to go back once again to the original equation, which is hydrostatic, okay? So once again, original equation, hydrostatic says dP is equal to minus rho g dz. Now I know this rho is not a constant. Gravity is still constant. This is fluid mechanics. Okay. Now in aero, gravity is not even constant, but this is not aero. This is fluid version of, okay. Gravity is constant, okay, but density is not. But we do know pressure is equal to rho RT, right?
Mm-hmm.
So you can say rho is equal to P over RT, right?
Mm-hmm.
So you just plug back in rho equal to P over RT. So now you're not going to deal with density, but you are going to deal with pressure and temperature instead. Okay? Now, what if the temperature is constant? That's called isothermal. That's what I'm talking about. What if this temperature is constant? Hey, this constant goes outside of integral. Here we go. I can finish up the integral and then come up with a different equation than incompressible case. I'm not going to do it because it's in the notes. Let's take a look. So that is isothermal pressure variation. Here we go. This page, what's that? Unit B to page 1 of Dr. H's fluid mechanics. Now, I don't know where in your own fluid mechanics professor's notes. But find out. Okay? No matter who's teaching fluid mechanics, that person must cover this. So this is the equation. If the temperature is constant throughout atmosphere, temperature is T0. Temperature doesn't change. Okay? So that means throughout this altitude, temperature stays constant. If the Z1 is a sea level, it's just a sea level temperature throughout. Is it a good assumption? Not really. I don't think so. I climb up Mount McKinney and then, oh, you know, I feel the temperature of Phoenix. I don't think so. No way. Temperature keeps changing. Actually, it keeps decreasing. If you go up and up and up, temperature goes down and down and down. It's fairly linear, but it just keeps decreasing. That's the real atmosphere. That is number 3. So number 3 is based on the fact that the temperature is not a constant throughout atmosphere, but we can model as a linear function, starting from sea level all the way to 11 kilometers. This is about 36,000 feet. Okay. But at that point, temperature stays constant from 11 kilometers all the way to 20.1 kilometers. This is like 66,000 feet. This is the model called the US Standard Atmospheric Model. Okay. Now the question is, in this region called isothermal area, you already have the equation, right? We can use this equation for that region. This is isothermal equation. So suppose if you pick up any height here and any height here and here, between those two heights, you can model the pressure difference using this equation. Of course, this is isothermal area. That's right. Question is this region. It's a linearly changing temperature. How do you do that? Temperature keeps changing linearly. So now you are going to, once again, go back to this equation, right? dP is equal to minus rho g dz. Again, everything is starting from same equation. Now the density is not the constant, so you're going to replace this with P over T, of course. P over RT. You are going to replace this density for P over RT. Now temperature is not even constant, but you can mathematically model this temperature as a linear function. And you can finish up integral. So you can come up with a different version of equation, which is right here. This is troposphere, sea level to 11 kilometer. You can use this as a function. Temperature is a linear function starting from sea level value temperature at sea level TA minus beta z. Beta is a lapse rate. So this is a linearly changing temperature with respect to the height or altitude from sea level up until 11 kilometers. This is called gradient region. But since the temperature is a function of z, temperature is a function of z. So this temperature right here can be modeled as a linear function. How's that? This is a linear function. So you are going to do a variable switch. Instead of integrating over z, you are going to integrate over t. So you are going to integrate from sea level to the given altitude or height z, okay, over the temperature for a given given value of sea level to the temperature value for a given altitude. Then you can finish up your integral, mathematically speaking. Then this is the equation. Go ahead.
Is beta usually just 0.00357 ranking?
Actually, if you go higher and higher altitude, it's going to be like this. Gradient region 1, gradient region 2, gradient region 3. So beta value is going to be different for
Okay.
each different.
It's just a property of the atmosphere, though?
It's basically the lapse rate, which is how much linear change you can expect for this region. In other words, from sea level up, beta value is that.
Got it.
But from this region, it's actually
Beta
negative
values.
value. Go ahead.
Is the lapse rate a value that we are expected to calculate, or is it a value that we would find?
Lapse rate is usually given, which is known value. That's what we're going to cover in Unit A2 of aerodynamics. Wait and see, you'll be excited. But here's the bottom line. I'm not going to lecture you Unit A2 unless you understand fully about this hydrostatics-based pressure variation in different conditions. Without that foundation, you probably have no clue. Okay, so rather than going home, I'm going to ship you back to fluid mechanics class once again, because that's what you need. You don't have a foundation to move on in aero. Okay, so let's avoid it. Of course, everybody should have foundation of fluid mechanics. This is it. So today, once again, I sacrificed my lecture of aero covering fluid mechanics. So this is Ernie's tip. Dr. H's fluid mechanics note B2. Actually, B1 also. B1 is incompressible density constant. B1, B2. That's what I'm showing here, by the way. So this is my fluid mechanics notes. You need to be all the way up. This is all about fluid statics. You can get this notes from course homepage, Unit B, right here. Let me just zoom in more. Click here. Unit B. It's all about fluid statics. If the fluid is not moving, what kind of pressure variation you can expect? It all depends on your assumption. Okay? Starting all the way from hydrostatic equation, which is this. This is hydrostatic equation. This equation basically says that dP equal to minus rho g dz, right? So this is basically dP is equal to negative rho g dz, because rho g is gamma. Rho g is gamma. This is called, what's this?
A specific
Specific weight.
SG is
Specific-
based on rho over rho water.
Specific gravity is different. Specific weight is this. Okay? How much weight do you have for a given volume? That's called specific weight. Wait a minute, didn't you do quiz one?
Yes.
You know it, what it is. Anyway, so what's the unit for the specific weight? It's going to be kilogram per cubic meter, right?
No.
You said no?
That's right.
Oh, Newton.
Newton per cubic meter, that's the standard, but you can say kilogram force per cubic meter. That's, you know,
You
we use that
could.
all the, well, fishermen do that all the time. Now you have to deal with those things. That's engineering. Fisherman says, oh, 2 kilogram. David, 2 kilogram is 2 kilogram. This is not a moon. Well, fisherman will never say that. But as you know, I mean, if you go to moon, of course, kilogram force will be different from kilogram mass.
Yes.
Big time difference, right? So you have to know those things. Anyways. But you know the property of a specific weight is different from density. Density is mass over volume. Specific, well, that's rho. Rho times gravity is a specific weight. So the specific weight is going to change under the different gravity, but the density never change. If you go to the moon and then step on the house meter saying, oh my goodness, I'm lighter. Of course, you're lighter, but you have same body mass, right? So those are different things. One is a weight, which is force created by gravity. The other one is a mass. Those are clearly different. So I think you are the only people who need to differentiate those things, but you need to, because you call yourself aerospace, maybe, right? Aerospace engineer, major aero track, you have to do it. Okay. So this is earnings tip. So this is just a summary here. It's just to summarize. So before we move into Unit A2 of aerodynamics, which is 100% YouTube lecture, you have to understand this, okay? US standard atmospheric model based on the fluid mechanics class is essentially we're dealing with same equation, which is hydrostatic equation. Now, the big assumption in fluid mechanics is the more, let's assume gravity constant because it's so easy. You don't have to worry about changing gravity with respect to the altitude. Because fluid mechanics, we always deal with, okay, near the surface of Earth anyways. Gravity, well, let's assume constant. We don't talk about high altitude at all. Now, that's not it for aero, okay? So the big change from fluid mechanics version to aerodynamics version is, of course, we're going to introduce now altitude. Altitude comes with different definitions. If airplane pilot says altitude, that is geometric altitude. That means if you have a tape measure, drop it down from your airplane, and how high you are flying, that's altitude.
AGL versus MSL.
So if you are space or astro track people, altitude means how far apart from the core of the planet. Planet core. I'm not the Ganga, but the planet core. Okay, planet core to whatever the location of your spacecraft is the altitude. That's absolute altitude. Okay. Now in aero, we are going to deal with two things. One is a geometric altitude. Typically means that measure the distance from sea level to the location of your airplane. It's called geometric altitude. However, gravity keeps changing, so we have to somehow incorporate that change. So we are going to employ something called geopotential altitude, and then use that into this equation. So here is the big issue. As you go through YouTube lecture, please understand what the heck is geopotential altitude. So get ready to answer that question. If professor says, hey, tell me, what is the geopotential altitude? You have a crystal clear answer, then you get a job at the job interview with a Boeing company, because people at the Boeing, they do those kind of things. I actually know a few people, and then I keep telling them, hey, ask those questions, you know. you can instantly tell this person have no clue, just pretending, or, oh man, this is real skill I want. Ask those kind of questions. Okay, tell me, what is Reynolds transport theorem? How much do you know? Just go ahead, and I'm waiting, listen. Then I'm going to make a decision if I give you a job, or you probably have no clue what are you doing, kind of. Okay, so be ready to answer that question. What is geopotential altitude? That is the key to understand Unit A2, because that's the big difference from fluid mechanics to aerodynamics project. Now, of course, gravity is not constant, but unless this is constant, you cannot finish up your integral. So we assume this is G0, which is a standard suitable value, but this H is a different definition of altitude. So the change in gravity is already incorporated within the definition of altitude. This geopotential altitude is fictitious, only made up for calculation of change in gravity. So airplane pilots, they don't need to know. You are the only one who knows what it is and use it in your calculator or calculation. Other people don't need to know. You are the only one who knows. That is engineering. There are lots of things only engineers should know. Oh, don't worry about it, because you are not an engineer. I don't even share this kind of information. You don't need to know. You are just a guy flying airplane. No, I shouldn't say that. Pilots are great. I love pilots, especially Professor Sean Gerald driving like a Swiss Army knife kind of car. Have you ever seen that the military truck always packed up? That's a pilot's car. Professor Sean Gerald, why are you driving this car? This is like 5 gallons miles per hour kind of, well, 5 gallons per mile. 5 mpg kind of car? My Corolla is 35, okay? Kind of thing. Anyways, pilots are great, but there are certain things engineers need to take care of. So let's just finish up because you're all here. Okay, because you're all here. Let's finish up Unit A1. Because you already know the homework due date, right?
Monday.
Monday. So that means I have to finish up Unit A1 somehow today. I almost forgot, my goodness. So let's take a look at the updates. Okay, so there are a few updates. Homework of Unit A1 is due Monday, September 13th. Before noon, please submit. Total 6 PDF files into the specific file folder says homework A1. Okay, you know how to do it. Good. Quiz. Of course, before you even work on quiz 2, why is quiz 2A? Must be Q2, sorry. Yeah. Q2, there's no A or B. So first of all, finish up quiz 0 problem 2. Okay, don't leave it, or just don't ignore that problem, because this problem is the basis of today's discussion. Finish up this one first, figure it out. I gave you answer keys. Then and only then, work on this. Okay, this is due Wednesday, next week, before noon. So everything on this quiz 2, is based on today's lecture. Go ahead.
So when we submit it, you want us to have it Q2, not Q2A?
Q2. This is Q2A? I don't know. The file itself is Q2.
Oh, okay.
Yeah. So I have to change it to this one. Yeah, this is typo. File is Q2. Sorry about that. I'll fix it today. Okay. All right, so let's just go back to Unit A1 notes, last page. Let's just finish up. Okay. All right. So this is the last page of Unit A1. Let's just quickly finalize this thing. Okay. So the air is flowing on a wing of Boeing 787 Dreamliner at cruise. Okay. The pressure and density of air measured was 3.25 psi absolute psia and 0.00075 slugs per cubic foot. Numbers are weird, isn't it? Who wants to use 0.00075? Because I'm sticking with standard unit slug. So this is probably the main reason why people want to pick up pound mass instead of slugs and then inches instead of foot, because it just produces better numbers, but it's not the standard. So you have to convert it to always to the slugs per cubic foot. But this is a nice problem because I didn't give you that weird unit. I gave you standard units. But actual quiz and homework, you may need to be careful about that. Okay. If somebody gives you pound mass in inch cube, you have to convert it to slugs per cubic foot. Okay. What is the temperature in degrees F? Not the Rankine. Of the air. Of course, this is easy problem. Let's get it done. Of course, you know that. This is almost like, oh, you don't have to do this in class kind of problem. But anyways, So pressure is given P. Okay, so this is 3.25 psi. So I'm going to pick up this number, plug into the calculator, right?
No.
The hell no, you know that.
Yes.
So that's just, how do you convert it?
Multiply by 12 squared.
Multiply by 12 squared, 144 P, no. Oh yeah, PSF over 1 PSI multiplied by 12 squared. Okay, so this is going to be 468 pound force per feet square PSF. PSF. This is the standard unit you want to do that. This is pre-processed. Okay, so don't pick up this number in your calculator. You have to use this number instead. Density is given as is, the standard unit, 0.00075 slugs cubic foot. This is a standard unit. I'm trying to be very nice of you, nice to you. This may not happen in quiz and exam. I don't know. It depends on my mood. If you're responding very nicely, I'm not going to challenge you. But if you behave like, pounds of pounds, what are you talking about? Well, I'm going to challenge you for the exam. Okay, so it's up to you. This is engineer's class. It's not fisherman's class. So temperature is P over rho R. So you can just plug in temperature to get the temperature. So T is equal to, okay, you're going to plug in pressure. Pressure is 468 pound force per feet square. This is a standard unit. Density is rho, 0.00075 slugs per cubic foot. What is Gus constant? Anybody?
1716 foot-pound per
So you
foot.
memorize.
It's like Rankin.
So 1,716 unit is foot pound slag ranking. So you have to be very careful about the unit. In other words, if you try to cancel out all the units, you realize, hey, wait a minute, ranking remains. So whatever the computed value here is associated with ranking. So if you pick up your calculator, punch the number, I'll do it for you. This is going to be 363.63, and then unit is, of course, ranking, because the ranking is the only unit you remain if you try to cancel out all of them. Okay? This is not what I wanted. You have to convert it to Fahrenheit. So final value is 363.63. Ranking. Subtract 460 and get you Fahrenheit. Oh, it's negative? Oh my goodness. Minus 96.37 degrees F. Holy. Do you think you can survive if you try to sneak into the cargo compartment, non-pressurized, or maybe inside of the landing gearbox? You'll be dead, guaranteed. Okay, so something you need to know. This is the cruising altitude of passenger airplane. This is probably transonic airplane. So high altitude, this is probably 36,000 feet cruising altitude. If you're not pressurized, I don't think you can survive. Just looking at the temperature alone, okay? So that's actually going to lead you to the next subject. Okay, next subject is, okay, it's going to be a unit A2, right? Okay. So if you go to course material is nicely lined up for the order of lecture moving forward. So we are done here. So now next step is, of course, we're going to take a look at unit A2, standard atmosphere. So this is entirely based on fluid mechanics, fluidostatics. That's the lecture for today. So make sure you finish your quiz 0 problem 2 first. Make sure you understand it. And then go through quiz 2. That's the real quiz. That is going to supposed to be set your understanding of fluid statics, fluid mechanics. Then and only then, go ahead and take a look at YouTube video lecture. I'm not going to cover this in class. And then, of course, this unit comes with tons of homework assignment. And then this homework assignment due date, I'm going to announce it sometime next week. Most likely do Friday, but I don't know. Because you have things to do for Monday, you have things to do on Wednesday already booked up. So next available day is probably Friday. So I think it's most likely Friday noon, but I'm going to announce it to you. But don't wait for my announcement. Go ahead and move on. So next class on Monday, we're gonna jump right into A3. Okay, get ready for it. Do you have any questions? Have a wonderful weekend. We're gonna see you back on Monday.
Thank you as well.
Finish reading, but
Yeah, I have to do that probably today or tomorrow.
to plug in the grade, polish report or something.
Then you're gonna know as soon as I finish. You can, but
12 hours. Got it. Thank you. Have a good day.
But the thing is, do we